Hi, I'm Philip Maymin of the University of Bridgeport. My talk is on computational religion. Good afternoon. My name is Philip Maymin from the University of Bridgeport. I know you all are here to learn about God. So there's two layers to this talk. One, we'll talk about God. We'll figure out the probability that God exists. We'll do machine learning on the Torah, all of that. But the meta purpose is I'll point out a lot of other talks go deep. This one is going to go broad. And you'll see lots of little tips and tricks of doing weird little things as we go along, like Hebrew typesetting, which Stephen mentioned. So Stephen mentioned there's computational X for everything. Today, X is religion. Wikipedia data, how to use fine textual answer to be useful. Careful things to do with Wolfram Alpha and hidden assumptions. How to use semantic interpretation. Can we do n probability of the new around stuff that's in there? How to delete stop words in other languages. Words as musical chords. Mail search, sequence predict. All right, let's get to it. So let's start with, does God exist? In Genesis 22:17, which everyone will be reading next week as the portion of the Bible, God tells Abraham, you will have so many descendants, more than the number of stars. No. Even more than the number of grains of sand. If someone says to you that, do you think they think there's more sand or more stars? Which one? Sand, right? You wouldn't say you'll have hundreds of descendants, no, dozens, right? It has to go up, right? So God made a prediction, a prophecy, that there's more grains of sand than there are stars, which seems bizarre, right? Because now that knowing what we know. Let me prove it to you. So, there's this great function I'm going to use from Stack Exchange, Hail Rutan, if he's here, but great function for highlighting. Here's every translation that I could find from this website of this verse where he says stars and sand. You can see stars always comes before sand. It's not a mistranslation. It's not a poetic justice. Stars always comes first. And we can plot it, and it always appears, the string position of stars always comes before sand in every translation into English. Well, let's compare it in the Hebrew. In the Hebrew, this is a picture. This top one is a picture of what the verse says in Hebrew. And this bottom one is if you just copy and paste the text. So notice something. The first word has this hyphen, right? But that first word appears on the left here. And all of these words are kind of backwards. Do you see that? It's a problem. In fact, if you look at the words, they are in order. The hyphen is the first one, and the second one. The ordering is correct. The typesetting is wrong. Make sense? Just the visual representation. Which Stephen mentioned something they're working on. Well, here's a little workaround. If we just split it by this, the sentences and then reverse it by the words, now it looks the way it should look, right? Agreed? Now we can highlight that, and we see that even in the Hebrew, right, Hebrew red, right to left, top, red comes before blue. So always more sand than stars. Yeah? Which comes first? Right, that's all. Right, but you wouldn't say, you wouldn't think that their sand is less. Right, if God is saying, you're going to have thousands of descendants. No, 2. Right? Right, it's additive, it's more. Usually it's a factor of 10 times more in typical Torah exaggerations, right? It's usually a factor of 10 or plus 1 or something. That's interesting. Well, how many stars are there? Anyone know? We could start off by thinking, well, from ancient times, what did people think? How many stars there were? And on Wikipedia, you can use Wikipedia data, get some text sentences, see the timeline of history. So around 1800 BC, that's the earliest star charts we know, there were about 17 or 18 constellations from the Babylonian star charts, which, by the way, do you know why we have 360 degrees? Babylonian star charts, eventually they solidified from 17 or 18 down to 12. Each one had 30 degrees. That gives us 360 degrees. And those are the 12 zodiac signs that we have through to today. In the Beijing, in the Dunhuang star chart, this is 705. This is well past any estimate of when the Bible was written, right? This is 700 years after the modern era. This is a beautiful star chart that was drawn at that time. And if you do find textual answer, here's another little clue. I want to search Wikipedia data for the Ptolemy's star catalog and for the Dunhuang star chart for how many stars there are, right? That's what I'm searching for. How many stars? And it's automatically figuring out the answer. Well, in Ptolemy, it's fine. It's in the Wikipedia text, and it'll say there's about 1,000 stars. But if you want to search the Dunhuang star chart, it's unfortunately in a caption of the image. So the tip there is don't just use the article plain text, but use the entire raw article wiki code and have it find the textual answer from there. And so it'll find it. So whether it was Ptolemy, which was when? Ptolemy was around 140, or Dunhuang around 705, they only knew about 1,000 stars, right? So how many do we know earlier? Only about 1,000. Well, suppose someone was a really good astronomer. How many could they have seen thousands of years ago? Well, Wolfram Alpha says the number of stars visible to the naked eye is about 9,000. Did you know that? If you look in the stars and you actually try to count them, you can't get to millions and billions and trillions, right, without a telescope. So that's what they could have seen. How many are there in fact? Well, let's just ask Wolfram Alpha. There's 10 to the 24th stars. The end. Where does that come from? It comes from how many stars are in a typical galaxy. If you search that, it'll say between 200 and 400 billion. And I used to think, and maybe you still did too, that the two numbers you only need to know for astronomy is about 100 billion stars in a galaxy and about 100 billion galaxies. So you multiply them out and you get some number. But it turns out in the past few years, the number of galaxies has increased, and we now have 2 trillion. We know that there are 2 trillion galaxies. So if we take, by the way, semantic interpretation is a nice function because it doesn't need to go to the cloud. It just computes it directly on you. So how to convert 2 trillion to 10 to the 12th. But here's the thing, those 2 trillion galaxies. The research was done by this fellow named Consolis. If we do find textual answer from an article published on Live Science about it, and ask how many stars are in an average galaxy, we don't get 2 to 400 billion, we get 100 million. Twice, right? Twice it says 100 million, not 100 billion. What? I was sure it was 100 billion. The mistake I made is the same mistake Wolfram Alpha made. Check this out. When you click on how many stars in a typical galaxy, it actually interprets as the number of stars in the Milky Way galaxy, our galaxy. And it turns out our galaxy is not typical. We're a pretty large galaxy. Congratulations. Most of these new galaxies that they've been discovering, and that brings it to 2 trillion, they're older galaxies that had fewer stars. The average galaxy now only has about 100 million. All right, so if we take these two interpretations, either from 100 million galaxies, 100 million stars per galaxy times 2 trillion galaxies, or at the high end, 100 billion stars per galaxy times 2 trillion galaxies, then we get that the number of stars is somewhere between 10 to the 20th and 10 to the 23rd. Make sense? So it's a range. All right, I know what you're thinking. If we're going to do the same process for grains of sand, you're going to lose your mind. We're not, don't worry. Wolfram Alpha tells you exactly how many grains of sand there are, and you can expand it, and it's correct. It knows it's Earth, not Mars. Everything is perfect. So boom, sand is easy. Sand there is this amount. Just need to evaluate it. So number of sand is somewhere between 10 to the 20th and 10 to the 24th. So those are the two numbers we have. They're both in the same range. Isn't that interesting by itself? Then the 20th and the 23rd. Can you imagine 3,000, 2,000, whenever it was years ago, writing a prophecy that predicts that they're even close? Because you can see maybe a few hundred, a few thousand maybe stars, but you can tell there's a quintillion, bazillion grains of sand, right? Like you wouldn't say, you wouldn't exaggerate to the effect of, I love you from here to here. No, from here to way, way, way over there, right? That doesn't make any sense. It's too much of an exaggeration, right? Stars and sand. So the first thing is that they're relatively comparable to within about an order of magnitude, which is amazing. Well, so which one is better? Which one is the truth larger? The way to answer this question, I think, is we have two effectively confidence intervals for them. So if it's a 95% confidence interval, it's plus or minus 2 sigma. So we can just do take the mean and divide the range by 4. That's 4 sigma. We can try, first of all, this new around function in the version 12. But maybe your luck will be better than mine. N probability doesn't seem to work for it. So even though it knows what an around is, you can't quite tell what the probability is. But no problem. We can just tell the number of the grains of sand is between those two convergences and the stars. Are you ready to find out the answer, the probability that God exists, that prophecy is for real? Ready? I'll scroll up so you can all see the big reveal. 89%. 89% chance God is real. Now, we can make a little website for people to change, because it's very sensitive to what you expect your estimates to be about the number of stars in sand. The key thing about this is the data bin. So it's really easy to create a new data bin and have everybody's answers show up afterwards. So here's God probability. Let's change the low estimate to 21 or something. Submit, and it'll tell you your God, and you're welcome to visit this page too. It'll tell you your probability right here, the orange dot, and everybody else's who's ever voted and the average. So on average, which has only been me so far, you're welcome to change it, has been about 73%. I used to have an error. I used to think that because of the billion, trillion, whatever issue, I thought that there was only a 2% chance of God existing. I was very depressed, but fortunately, everything worked out. All right, let's look at some visualizations in Hebrew. So we'll have books. This is, you can see the characters are in Hebrew, Bereshit, Bara, and so on. This is from the Leningrad Codex, which is 1,000-year-old, the oldest complete manuscript of the Hebrew Torah. It has 304,850 characters. If you ask Wikipedia how many letters are in the modern Torah, they say 304,805. I swear, maybe 10 times I saw these two numbers, I thought they were the same. There's a difference. The difference is about 1 basis point, right? 1% of 1%, which is de minimis. And there are some differences, but the differences are something like a vowel placed here or there, like a vav or something. Okay, so one problem with word clouds are great, but what's the most commonly occurring word in every single one, the first 4 books, and what's that first word, the biggest word? You know the word, what is it? Oh, you see, I share. But what about these ones? Et, what's et? Exactly. It's like nothing, right? It's almost like it. It's some kind of pronoun or something. It's a stop word. But there's no English, there's no Hebrew delete stop words. But we can create it. How? Let's take all the stop words out of the word list. So what are we left with? Non-stop words. Take the complement. Boom, we have all the stop words the Wolfram language uses, because it's not in the documentation anywhere. You don't know what the list of stop words are, but now we know. Where? Oh, really? Oh, okay. We should put that in here somewhere, no? Not here. Not there. But this is where it belongs, right? Okay, I believe you. I believe you. But there's still no way to translate it, right? So we can translate it here. We'll just translate word by word into all 3 possible Hebrew things, put them all together. Now we have Hebrew stop words, and boom. It takes a little while to calculate, so I'll just show you what happens. It gets rid of all the ets and everything else. Great. Now that looks much nicer. All right. So we watched the Torah. Let's listen to the Torah. So every week around the world, everybody who reads the Torah reads the same parsha, the same Torah portion. This is the Torah portion for this week. We're going to play it. It takes 15 seconds to play it. Each word is a chord, right? Each letter has a sound, and each word is a chord. So we're going to put them all together. You can listen to the whole Torah this way, and it's kind of interesting to hear the differences between the books. But here, the only thing I think you'll really hear is, see towards the end, the words become shorter, so the chords will play a little faster. So let's see how that works. Not very well. I don't know how standard. There's no way to turn the volume from here, right? Anyway, all I did was take the character code and subtract the middle character code of 1501. I think that's what it was. Yeah, 1501. So then it just goes on a C scale. Sorry, we couldn't hear it. Yeah, maybe we can do this. So you won't see it, but you'll hear it. Here we go. What? Oops. Typo. Can you hear that? Okay, here we go. Action. Oh, it's something with my computer apparently. All right. Apologies. I'll sing it to you later. Okay, so let's do machine learning on so here's the goal is to use the original Torah to generate new verses from the Torah and see if it can fool people. So we'll do teacher forcing, which is the same as the docs, but just like a couple more options we'll add in. Here's the source documents. We have the name of the book, the chapter and verse, and the text. So we could put the Torah all together. Here's some random samples of the way the machine learning will take the inputs. Now, I don't know how you guys do neural net training, but the way my mom told me to do it is you always start with a small one first. So you just start with like a 60-second training, which is nothing. There's no results. But now you have the basics. And then every time you train it, you just put it on a loop to train. Because the problem is your computer will break, right? You've trained it for 48 hours, and then it broke, and you lost everything because you forgot to save it. So make a loop, save it every whatever, some number of hours. I used to do it every hour, which is great during the day, because you need to check your phone every hour. But at night, when you wake up, and you have like 20 messages, it's annoying. So do it every 4 hours. If you do every 4 hours, you can send yourself a mail message with the results, and then afterwards you can just collect those results with the new mail server and mail search. So here's all of those messages I sent myself, and once you get that in a data set, you just rejigger them, and you have all the results. So this is after 4 hours. This is the lowest validation error and the final validation error, and here's what it says. So here's a sample from it. And Hashem said, "I know that Hashem, the Israel, after Thayer forts." That's frustrating, right? And you can keep going down, and after a while, it seems like it's a little bit better, but then you still defiled. It's not a word. I got swears in some of them. I cleaned those up. Some of them are just anachronistic, like Hashem spoke unto Moses and unto Aaron. This is after 92 hours. And she, berond, I don't even know what that is, but whatever you don't want to get beronded by a female god. And Hashem speaks to Moses and unto Aaron, that's fine, but then Joseph? Where did he come from? They never appear in the same verse. So the problem is after 100 hours, I didn't get much improvement at all. We're still having things like oit, X, ye, rain. It looks like it's programming. Let's see if we can get some better results. One thing I was thinking is, well, there's new functions, and what is the typical way of working with Wolfram language over several years? Right? What happens as things evolve? You work on a project for years and years and years. You have a huge code base that does something really remarkable, and the next version comes out with a one-line solution. Right? It's wonderful, but also sad. So sequence predict is a great function. You just feed it the entire Torah. It thinks for 40 seconds. That's it. And boom, it's done. And then when you predict from it, it's not as good as neural network, but it's really fast, and it's useful for some other things I'll show you. If you just do random next elements, it's equally garbagey, right? It's not very good. The other thing you could do is a next sequence. What's the difference? Random next element is every single time it'll create a new element, totally randomly, like a random sample. Next sequence, it's more like Monte Carlo, right? It's going out for lots of different sequences and seeing which one of them total has the highest probability. Does that make sense? The whole thing together, not just one at a time. And that you often, unless you change the temperature, you end up just a loop, right? Hashem spoke, saying speak, speak, saying speak, speak, saying speak, speak, saying speak. But this got me thinking that the right solution is something like reducing the small probabilities of things that happen. So we can generate a sample. I'll regenerate this from scratch. Two things here. One, we can generate a sample of the information that's coming in, given whatever you want to start with, but only with top probabilities. So there's this parameter of top probabilities that you could take as a property. If you just take random sample, it takes all probabilities. Wouldn't it be nice to have a top random sample, just like you have a top probabilities? Well, so that's all this does, is takes a top random sample. So you feed it with anything you want. Like if you just start with and, it'll think for a bit and say something, okay, that's useful. Abraham took their front. That looks pretty good. But you can also ask questions like, and at the Wolfram Technology Conference, and it'll feed it. Now imagine you had this, as a Microsoft Word or Google Doc plugin. It read all of the stuff you've written so far and it just suggests entire paragraphs that you can then add. Wouldn't that be nice? Before all with the base of these, no, that doesn't make any sense. So you could just delete it, append some new ones, and then against thee from Hashem thy God. That's a pretty good one. And thou shalt put, the variant. So then you could just delete the rest, right? So you can have a combination of slightly human editing with automatic additions. And thou shalt keep them and say unto them when ye became one. Hey, it's not bad. Thus shall ye stand by the camp of Wolfram. Very good. So let's do a survey. I'm going to generate all of these things, make a bin. One of the things I did, so I spent almost 3 hours generating both random samples and new generated samples. Got 10,000 samples of those. But also the next thing you can do is classify those samples. I know some of them came from the original Torah and some of them were machine generated, right? So I can feed that into a classifier, and the classifier does a really good job. It says these are obvious and these are confusing. So let's just look at the confusing ones. Maybe that'll be even more confusing to human people. Here's for an example. This is the correct classification, and this is what the prediction was. So it's not from the Torah, but the classifier thought it was, because Hashem spoke unto Moses, saying the Canaanite and the Hittite and the Perizzite and the Canaanite and the Egyptians. It sounds real, right? Totally made up. Okay, here's let's do a quick one and then open a question. So here's the survey. This is 10 out of the 10,000 questions. And you raise your hand if you think it's from the Bible. And he took us up his parable and said, from Aram Balak bringeth, definitely wrong, right? Oh, wait, maybe it is. The king of Moab from the mountains of the east. Come curse me, Jacob, and come execrate Israel? Probably not, right? Let's go probably not. And the burnt offerings were strangers, which again, I said, whatever saw the tabernacle, thou was not seen the basket. What do you think? No, right? It doesn't have a certain like consistency, right? Perfect. So it's a factual error, stupid machine learning. And Hashem said unto Moses, if I may prolong your days upon land which I swore unto the fathers. That sounds good, right? Yes? Any disagreement? All right. One thing just to point out. When you're doing, this is an asks within an ask function. If you're doing a random survey and you need to remember some random number, you have to put an ask display after your first ask assignment of the random number. Otherwise, it'll never update its data thing and it'll generate new random numbers. It's a little bug. Not bug, it's just it's a weirdness of the way you use it. And when any man might make the waters upon the tent of meeting and come forth out of Egypt, shall not be. What do you think? Yes? Seems reasonable, right? At least there's a logical coherence to the entire sentence, right? Israel hallow unto Hashem, having his unclean. No, right? For it is no vain thing for you, because it is your life, and through this thing ye shall prolong your days upon the land, whither ye go over the Jordan to possess it. Who says yes? Who says no? Oh, that's a yes, okay. And Hashem spoke unto Moses, saying, speak unto the congregation, saying, get you up from about the dwelling of Korah, Dathan, and Abiram. Who says yes? Who says no? Okay, that's a yes. And Hashem spoke unto Moses, saying, take it upon his house, and he called the name of it the children of Israel. Yes? Okay. All right, two more. Just shout it out what you think. And I will bring the land into desolation, and your enemies that dwell therein shall be astonished at it. Oh, it's confusing. Who says yes? Who says no? Ooh, that's a close call. I'll say yes. Astonished is a funny translation. And they made their land and saw that he toucheth the mount, and the names of the sons of Joseph from the land of Canaan they come. Who says yes? Who says no? Majority seems to be no. All right, let's see what our results are. Oh, we only got 5 out of 10 right. That's not good. Wow, that's crazy. We thought, okay, so Hashem, if I prolong, where's that activate one? Or astonished? Oh, it was in the Bible. The astonished one was in the Bible. Good job. Okay, questions? Thank you. Yes. Oh, thank you so much. I was very disappointed with machine learning. So machine learning seems to very quickly give interesting results, but then it tapers off, and it loses a lot of the magic and logical coherence of human speech. So I'm hoping that maybe I mistrained it. Maybe I need to train it more. Maybe the combination of training and reclassifying will work. I don't know. Yeah, please. I don't have a GPU. Yeah. Yes, that's a great point. Actually, I trained this in the cloud with the GPU. Of GPU, yeah, yeah. It's the same one from the docs, teacher forcing. Yes. Just tell me where to go, I'll be there. Any other questions? All right, Baruch Hashem, thank you very much.